It is late November 1967. In a field outside Cambridge, a sprawling radio telescope is listening to the sky. The data comes out as ink on moving paper, meters of it, read by hand. A graduate student named Jocelyn Bell is going through the charts. She switches to a faster recording speed, and the smear of noise resolves into something impossible a pulse, then another, each one arriving about every 1.337 seconds, steady as a metronome. Nothing in the known universe was supposed to do that. Stars glow, they flicker, they do not tick. The source was catalogued as CP 1919. But before anyone published a word, the team gave it a private nickname. They wrote LGM1 on the file, shorthand for Little Green Men. It was a joke mostly, because at that moment nobody had a better explanation. To understand what they had actually found, you have to go back 33 years. In 1932, James Chadwick identified the neutron, a particle with no charge sitting in the heart of every atom. It was a laboratory discovery made with laboratory equipment. 2 years later, two astronomers took that particle and did something audacious with it. Walter Baade and Fritz Zwicky proposed that entire stars could be made of the stuff. They suggested such objects are born in a supernova when a massive star dies. The core collapses. What survives is something denser than anything in human experience. They called them neutron stars. It was for decades an idea and nothing more. There was no way to see such a thing. It was too small, too faint, too strange. Most astronomers filed it under theoretical curiosity and moved on, which is exactly where the story sat until a young researcher started reading chart paper by hand. And here's the thing about that ticking signal: the team's first instinct was not celebration, it was suspicion. A perfectly regular signal is a red flag in radio astronomy. Regularity usually means something human: a faulty amplifier, interference from a passing vehicle, a badly shielded piece of equipment somewhere nearby. So the group worked to eliminate every mundane explanation they could think of. The pulses kept coming, on schedule, tracking the sky like a star. Whatever it was out there, not in here. On the 24th of February, 1968, the discovery appeared in the journal Nature. The paper carried five names: Anthony Hewish, Jocelyn Bell, John Pilkington, Paul Scott, and Robin Collins. It was the first known radio pulsar. Within months, the interpretation began to settle. This was not a signal from another civilization. It was a corpse, a collapsed stellar core, spinning, sweeping a beam of radio energy past the Earth like a lighthouse. Bott and Zwicky's discarded idea had just walked into the room. A theory from 1934 had been confirmed by ink on a roll of paper. 6 years later, that discovery won a Nobel Prize, but not for everyone involved. In 1974, the Nobel Prize in Physics went to radio astronomy for the first time. It was shared between Anthony Hewish and Martin Ryle, with Hewish honored in part for his role in finding pulsars. Jocelyn Bell Burnell was not included. The graduate student who first noticed the pulses on the charts, who pushed to understand them rather than dismiss them, received nothing. The decision provoked argument almost immediately. Astronomers have questioned it ever since, and the questioning has not really stopped. It has become one of the standard examples in any discussion of how scientific credit is assigned, who gets named, who gets remembered, and who does the looking. Bell Burnell herself went on to a long and distinguished career. The debate around the prize, though, outlived the controversy of the moment. It became part of the discovery's permanent record. But set the politics aside for a moment. What exactly had she found? Because the object itself is harder to believe than the story around it. Take an ordinary neutron star, not an extreme one, a typical one. It holds roughly 1.4 times the mass of the sun, and it packs all of that into a sphere about 20 kilometers across. 20 kilometers, that is the width of a city. You could drive across it if driving were remotely possible. The sun, for comparison, is over 1 million kilometers wide. Squeeze that much material into that little space, and you get an average density on the order of 10 to the 17th kilograms per cubic meter. There's really only one familiar thing that dense: the inside of an atomic nucleus. So a neutron star is, in a rough sense, matter crushed back down to nuclear density on a stellar scale. Bott and Zwicky imagined this in 1934 with almost nothing to go on, and these objects do not just sit still, they spin. The first pulsar took 1.337 seconds per rotation. That turns out to be leisurely. Consider the fastest one we know. It is catalogued as PSR J17482446 AD. It completes roughly 716 rotations every single second. An object the size of a city, more massive than the Sun, turning that fast. It was found in the crowded globular cluster Terzan 5 using the Green Bank telescope, and the discovery was announced in 2006. Then there is a pulsar with a paper trail stretching back nearly 1,000 years. In the year 1054, observers on Earth recorded a new light in the sky, a supernova. Its wreckage is the Crab Nebula, and at its center sits a neutron star spinning about 30 times per second. One rotation takes roughly 33 thousandths of a second. This is why pulsars became tools rather than curiosities. Their beats are so stable that astronomers use them as clocks, precise enough to detect tiny disturbances in space and time. And in 2017, two of these objects did something that answered a completely different question. On the 17th of August 2017, the LIGO and Virgo detectors registered gravitational waves, ripples in spacetime itself, from a pair of neutron stars spiraling together and merging. The event was labeled GW 170817. Within seconds, gamma ray satellites caught a burst of high energy light from the same event. Then telescopes across the world turned to look and found the afterglow, a fading source called AT-2017 GFO, a kilonova. This was the first time the same cosmic event had been both felt and seen, and the glow carried information nobody had been able to obtain before. Analysis of that light showed heavy elements being assembled in real time, built by rapid neutron capture. Strontium was later pinned down in its spectrum. Two collapsed stars had collided and manufactured new elements in the debris. A question about the origin of the heavier entries in the periodic table had a direct observation attached to it at last. 50 years separate those two moments. A student squinting at chart paper writing little green men beside an unexplained tick, and a merger detected by gravitational waves watched by observatories on several continents, revealing where heavy matter is forged. The line between them is unbroken. The joke on that 1967 chart was never really about aliens. It was an honest admission that the observation had outrun the explanation. That is often how the most important results arrive. Not as an answer, but as something that refuses to make sense. A theory dismissed for 33 years turned out to describe real objects, spinning hundreds of times a second, dense as an atomic nucleus, keeping better time than almost anything else in nature. If you value this kind of story patiently told, consider subscribing. There is a great deal more sky to account for.